the slides and also the data sets and codes are provided. So there is a folder here for linear regression and India data. You can download that data. So I'll directly show you the data file here. So this is the Redshift sample file I uploaded. It has about I think 1200 records for we have 2400. So again, we can use SPSS to get the data, or you can use R if you prefer that. I just want to show it to you in SPSS. I prefer to use that one. Description of the variables is provided in a separate node file. So we'll refer to that as needed. So basically, this is the data view, and SPSS, if you have not used, it's like glorified Excel. It looks very similar to Excel, just that you have two sheets. You have a variable view and a data view. This is where all the data from this file is provided. So you have the stop, the route. This is a combination of cluster ID and stop ID. So for you, the important variables you need to look at are Y and log Y. These are hourly demands in the peak hour. Okay. So what we'll do is we'll do some models analyzing how log Y, which is the demand, because we can start looking at the Y also, but Y does not look like a normal distribution. That's why usually we take a log. So let me show description of this. So let's look at descriptive. So the simplest thing would be doing descriptive. You can look at Y, for example, like add these. You can look at the data set and come up with it. So you'll see that the mean is for Y is about 28. The range goes from 1 to 3. Okay, so all of these stops have some ridership. I think they added 1 to the ridership numbers so that if they take the lawn, there is no ridership which still remains 0, okay, not infinity. So that's why these numbers are like that. So the minimum is 1. That doesn't mean every stop has ridership, it's just that it is actually Y is ridership plus 1. Okay, and so because of the range, when you have such a large range and a lot of them will have zeros. So if I do the frequency for this one, and we don't want to do frequency in general, but I'm going to just show you for if you look at Y, you'll see about 4% of data have 1. So very few of these stops actually have zero ridership, which is good. So you start looking at some of these characteristics once you're given a data. So it's possible that if you're looking at low volume systems, you'll have 30% of the stops will have 0. If you're looking at any system of transit in the southern part of the United States, for example, probably 50% of the stops will have zeros. So depending on what system you're using, the method we use will change. Okay? Because if you have a lot of zeros, you need to figure out how to handle the presence of extra zeros. Here there aren't a lot of zeros, so we can directly use. So you can look at. You can also draw histograms if you want to see that. And you want to see the for the log Y variable again. The good thing about the log Y variable is it narrows down the range. So instead of going from 1 to 332, we now have a variable that goes from 0 to 5.8. So then we can start adding independent variables to understand. So when we are looking at a linear regression model, what we are doing is we are saying the ridership variable, the dependent variable is a function of other independent variables. So you are writing Y is equal to beta X and you are trying to find your betas. Okay, so we'll talk about the exact mechanism of how to find the betas in the class in the next session. But here I want to show you how we can do this. So I created a this is again if you have not used how many of you have used R? Okay. So what I'll suggest is go ahead and install R Studio and R Tools, and then you will be able to run it. So I'm giving you the code, so you don't have to code anything. You just open the file. If you install the software R Studio and R, it will work. So just look at how to install R Studio. A lot of things on YouTube or on Google, you can find that. So just install that, and then here I'm providing you different approach. So this is where you will provide the name of the data. So I gave you the CSV file. You just have to. It's already there. So you it should if you have the code, the script and the data set in the same folder, and you download it, both of them will be in the same folder. So it should automatically access that. Otherwise, you can change your directory, but usually it should pick it up on its own. So you can do the first thing I'm doing is just doing the means of the data just to get an idea of whether the data loaded correctly or not, and then we can do a lot of recoding on all of that. But this is the linear model. Again, I will explain how to interpret this. For now, I'm just giving you a structure. So this is your dependent variable. And then I'm identifying 5 or 6 independent variables. So the way you specify your linear regression model in RStudio is simply LM is going to let it know that it has to do linear regression. This is your dependent variable. And whatever you want to use as X. So Y is equal to beta X. X can have X beta 1, X1, beta 2, X2, and so on. So these are our X's. Simply that. Okay. So if we have this. So this is the model out. So it's running the linear regression model. So this is the dependent variable. These are your independent variables. Again, I'm just giving you some random variables here. You need to look at what these variables are, interpret and all that. So basically the code will run. So now what I will do is even before you run this model. So this is how you can run a linear regression model. But even before you run this model, I want you to look at the distribution of the variable. So if you look at the different variables here, there are what's called frequency variables. So if you think about ridership, right? What is one of the most important variables in modeling ridership? If I'm, let's say, modeling stop level ridership, what would be the most important variable in modeling ridership? But for let's say I want to model ridership for 3 hours, the peak hour. So what determines ridership the most? Any other thoughts? The transit service frequency or headway between the right. If there's only one bus coming, you can have all the accessibility you want. The people are not going to. So accessibility is important, but I would say the primary factor is frequency. How many buses go through that stop in that 3-hour period is very important. Now, is that a truly independent variable? Because every transit agency, when they're determining the schedule, it's not like they're going to put a bus every minute in the part where there are no people, right? I mean, if there is a rural location where there is probably 5 people who want to use transit, it's not like you send a bus every minute. You have high frequency locations, high frequency services in locations where there is going to be high frequency demand, right? So it's like a chicken and egg. So we have very high demand. So there is very high service. Now, if you run a model, you will say, oh, if there is a very high frequency, there is high ridership. That's not true. So you have to be careful. So whenever you look at any literature, any paper, they will say frequency is very important. Yes, frequency is very important. But what about the transit agency's thought process in saying this is a route where we will have a lot of demand? There is what is called self-selection. Frequency is a self-selected variable. Because we know a lot of vehicles, a lot of people will use the bus at that facility, so they put high frequency. So it's not a truly independent variable. So there are ways. Again, for now, let's ignore this issue. We'll talk about how to handle that. It's a complication on models, right? When you look at any linear regression model, y and x should not be correlated. You can do y equal to beta x only when y and x are truly independent. But again, this is an example where it's not the case. Your headway is determined because you expect some level of ridership. Okay, so there are ways to correct for it. We will talk about that. And here, there are different variables. I'll show you here, for example. So this is the frequency. So the variable subfreq is basically frequency of the subject route, and it captures buses per hour. So there could be 2 buses, 6 buses. So let me show you the distribution of that variable. Here. So again, less than 1 for a lot of records. So you will see that the number of buses per hour for some of the stops is less than 1, which makes sense. But then as you go up, you go to 2, even 3, up to 16. Okay. So what we are seeing is there are some stops where you are getting 16 buses in a 3-hour period. But there are some stops where you are getting much less than. Okay. So this is a linear variable, right? At some level we have a continuous value, but one could argue that there is some potentially non-linearity in the impact, right? So if the number of buses is up to 1 or 2 per a 3-hour period, it's like it's coming only once in that whole time period, right? You can say that the frequency is 0.4 per hour, or in 3 hours there is 1 bus, right? Pretty much. So the impact of frequency would be non-linear. So up to some point, frequency has a linear impact, but then it can go up. So when you know there are 3 buses every hour, I feel more comfortable using that system, because I know even if I miss one, I just have to wait for a few minutes. I get. So it could be the impact of headway could be non-linear. So that's why they created these 3 variables. So they have 3 separate variables. These are called spline variables. So if it's 0 to 3, it's exactly the same variable. There's no change. If it's 3 to 6, you have frequency minus 3. Okay, if it's more than 6, you create minus 6. So these variables are created to see if there is an additional impact of higher frequency. So this is linear up to 3. After 3, this still continues. This effect still continues. There could be additional effect for 3 to 6. If you look at the third one, this continues beyond 6. There is additional effect beyond 6. Okay? So this is called a spline model. So you can think of this as a way to capture, maybe if you are between 3 and 6, on top of the linear effect, there is an additional linear effect. Okay, because it is more, or it could bring it down. It could be positive or negative. The effect could be positive or negative for these 2. So if it's positive, what it means is, if you have more than 3 buses coming, the jump in ridership is more higher than just increasing from 3 to 3.1. So when I move from 3 to 3.1, there is positive effect from here. There is an additional positive effect from here if the coefficient is positive. The coefficient is negative. What it tells you is, after 3, people don't care. It actually does not contribute as much to ridership, but we'll let the data show. Okay, so this is that. This is the same kind of variable, but on top of 6. So instead, so the way it's characterized, if you just have this is, let's say, the frequency. So if frequency increases, you are increasing rate. But what I'm going to do there is, I'm saying at 3 and at 6, this slope can change. Maybe it goes up like that, up to 6, and then maybe it lands up. I mean, there's only so much number of buses can do, right? If you're getting 12 buses or 15 buses, maybe it doesn't matter after a point. So what that means is you will hit the maximum at a particular point. After that, it just tapers down. There is no additional benefit. So to a particular stop, if you get 6 buses or 7 buses or 12 buses, it's the same effect as getting 6 buses. It could have again. So this could be potential case. So what we are doing there is we are saying the slope changes at 3 and at 6 it changes. So now this change could be positive, or like I'm showing the way I'm showing it here, it is negative. So what that means is it goes linear up to here, goes up and then tapers down. So you can think of this as a relationship like this. But figuring out this relationship is complicated. But if I break it into pieces and say, okay, this is a line, this is a line, this is a line, I am specifying these three as small lines. So you can see, you know that based on what we learned about polygon, any polynomial figure can be approximated with lines as long as you take enough lines. Okay, obviously you can take more lines, it will just increase our burden. So here what we are doing here is we are saying this is a non-linear curve of relationship with frequency and headway and ridership. So we are plotting that relationship. Typically what you do is you make an assumption it's linear and you do only one line, which most of the time is off by line, right? Because it's not possible that if I keep increasing frequency blindly things will happen. And also at the lower range, maybe frequency does not matter. If whether you have 1/10 of a bus coming an hour or 1/20th of a bus coming at an hour, if it is less than 1 per hour, maybe frequency does not really matter. In that case, maybe people decide to take the bus purely based on accessibility and need. Okay, so to assume that this whole thing is linear sometimes can be wrong. So that's why we can try different structures where we allow for a piecewise linear function. This is what is captured. So the variable creation described there is a very efficient way of doing it. It actually does not need a lot of work. All we are doing, instead of doing beta times frequency, you create 3 variables like this and you have a piecewise linear function. And these variables can be created very easily. The code is here. All you are doing is this, you don't change anything. Okay, if observed frequency is less than 3 buses, it's per hour is equal to 3. Yeah. So if it crosses 3, this stops at 3. Okay. Now this one will have frequency minus 3. Okay, all you're doing is taking off 3. And if it crosses 6, it becomes 6. So if it is between, if the frequency let's say is 4.5, okay, this value will stop at 3. This value will be 1.5. This value will be 0. If the frequency is 7, this value will be 3, this value will be 6, this value will be 1. That is how you create these 3 variables. Okay, we are just converting the single column into 3 columns following this logic. So if it's less than 3, just copy it, don't change anything, put these 2 as 3. Okay, if it crosses 3, this is simply 3. This will be whatever is the value minus 3. If it's less than, if it's more than 6, just make this 6 and go. You change. So that's that. So basically we are creating 3 categories of variables which handle the 3 regions that we are interested in. Okay, so that's what is being created. Okay, and then there are a lot of other variables that they created. I think you might have to look at the paper for fully understanding all of these. So they are looking at, they looked at the network and identified if there are competing routes for that stop, okay, or complementary routes. So they created these variables for us. Okay, so we can look at how many fully and partly complementary routes. So again, all of these might not be significant. Maybe 1 or 2 of them can be significant. So this they put an effort in identifying at the stop level what is the interactions on the network. Then there is also interactions with metro. They looked at how many of them are complementary, how many of them are competing. Again, this would require a lot of work to figure out which routes are actually complementary. Because again, there could be partial complementary nature. Partially, if you have a bus route and that's perpendicular, then you can say that they are complementary. Right? If there are both of them are parallel to each other and are covering the same neighborhoods, then you can start saying they are competing. So depending on that, I think this was a subjective classification of variables. So it must have been a lot of work to figure out which routes are complementary and which routes are parallel. Then they also looked at access to downtown. So they looked at number of downtown stops, downstream stops that were accessible from this stop, and so on. So they created these variables. They also had some stop level variables. So they had plan of population, plan of employment, commercial, industrial. They would have tried, and I think these are the variables that ended up being significant in their models. Okay, so basically the idea is you can start looking at some of these and consider adding them in the model once we go through it. Again, I'm not asking you to try it out yet. Basically, this is the formulation. The formulation is right here. You can pick the variables from that file and put them here with a plus in the middle. These are your x's, x1, x2, x3, x4. It will automatically add a intercept and run the model. Okay, that's how you can get the coefficients. So these are the coefficients here. So what this tells you is between the variable 0 to 3 has a coefficient of 0.66. It's a positive coefficient. What that means is if the frequency is higher, you will have higher ridership in this case, as you would expect. Any questions? Okay. So you can also look at the other codes. There is binary logic, multinomial logic OL. Again, I will go over all of these in class, and maybe because we not finished that part of it, we can look at that. And another thing I want you to do, some time to let you know. You get 2 slides from module 2, so I'll finish it so I can start methods in the next class. We'll be a little ahead. Again, this is building on what Dr. Agram mentioned. So again, we need supplementary data. When it's not enough to just have ridership data. If you have ridership data, that's our dependent variable, right? That's our y. We still need the x's that we need to look. So some of the attributes that we need are transit system operational attributes. So average headway. Or again, you can introduce this in different forms. You can use it as a headway, which would be gap between two buses arriving at that stop. Or you can look at frequency. You can convert that as a reciprocal of that and say in an hour 3 buses are coming. Or you could use the minute. So it's up to us on how we want to decide. Accessibility indices, we need information on transit accessibility. So how many bus metro train stops are there? How close are they? And what is the length of bus metro train lane within a ward or within the zone and so on. Then transportation infrastructure is important. Roadway length by functional classification. So you can look at how many expressways are there, how many arterials, collectors are there, what is the bike lane length, and also finally distance to central business. All of these are important. And other things such as number of parks, area of those parks, residential area, commercial area. Again, it could be commercial parcels or area of commercial parcels, retail, government, distribution. Again, depending on whatever information is available, employment density. There's another metric called walk score. I don't know if an equivalent metric is available in India, but basically what it represents is how walkable is that neighborhood. Okay, so we would consider whether there are sidewalks, whether there are traffic crashes happening, safety is mentioned or not. So based on that, some of these things we can. So this is an example list. This was one of our older papers in 2016, so it's already 9 years now. So we looked at these groups of variables. So we have stop level variables. So we were modeling ridership by time period. We had ridership for the AM, PM, off peak day, off peak night. So there were a lot of time periods, weekday, weekend, and so on. So we looked at headway. So this information is not always easy to get. So sometimes because bus frequency changes by time of day, if the agency that you're working with has that information, it is great. So you can then incorporate that. We had that information. We looked at how many bus lines are passing through each stop, so the number of routes using the same stop, we looked at that. And if if there is a night bus that passes through stop, so these were some variables we looked at for the stop level variables. Around the stop, transit variables that we looked at included number of bus stops, metro stops, train stations, bus line length. You'll see that the meters change because these are all the significant variables. So we tried 200, 400, 600, and 800 for everything. For all of these variables, we tried all 4 buffer sizes, and the values I'm showing here are the significant values. Okay, so here bus line length, and as all of you students know, most of the work was done by my student. So these are, he is the one who ran the models for all of these variables, and so 200, 200, 600, and then we also looked at metro line length. This is a TSB variable, so this does not change the buffer size, right? So because we did not have it in the, we used that as a better indicator for us. We also had reserved bus lane length, and then we also looked at infrastructure around the stop. So the major road lengths, highway length, land use. So you will see park area in different buffers, number of parks, commercial enterprises. So all of these we looked at in as independent variables in our model. Okay. So again, it's always good to have an exhaustive set of variables that are possible. So if you don't have a particular variable, obviously you cannot consider it. So if you have that variable, if the JS layer is available, you can start looking at that from that perspective. Okay, so we did a webinar for creating like some sound. How we create these variables. Again, the slide deck for this is also available. Just again, I know some of you might do this already, know how to do this. Some of you might not have looked at it. So he's the one who does this better than me. So I am doing this video for you.
Yeah, property will change. So how can I define jobs? Jobs can be defined as the number of jobs as known from points. The employment data for the University of London in 2016 was strong. These data contains information on the employment of individual aged 20 through 64 years. These data were partially included as a structure file using the unique and created by continuing in census records. Now let's discuss the case section issue. In our study, CUT was included using jobs
So here what we're doing is we're computing job accessibility. So instead of a static buffer, we're actually looking at if you start driving from that location, how far can you go 10 minutes in all directions? Okay, so it won't be a circle that way, but yeah, it's a network distance that way.
We use the minute runtime for our object device as the aggregate threshold. The driving distance was computed using the day period, and it must have been considered 8 a.m. on Wednesday. State network of Korea has been used to draw driving area for both driving time and distance. 2011, to be the system state network of T02 Data was used. So, to estimate the driving time, we use state network.
Maybe 5 minutes we'll finish it.
Then we define speed for a stream from the info category. In our network file, we have these categories, and we will select a fixed speed for a particular speed category. For example, if the speed category is 65 to 80 miles per hour, then we will consider the speed as 70 miles per hour for that particular speed category. So that is our network shapefile that is speed. If you open the data unit for the axis, you will find a speed category, and based on the speed category, you have to create a speed column. Then you also create a length column, create the length of the string in miles, and once you have the speed and the length, you create the proper time for each place, and it will be then you will create the network, create the network on your analysis on this, and you have to follow these steps. First of all, you have to go to Windows, then say catalog. And once you open the catalog, you will get the road network shapefile. So this is the road network shapefile, that's speed. And then you have to right click on the shapefile, and you will find new road network dataset. And you have to select it and follow the steps as we explained in detail in version 1. And once you complete all the steps, you will create the network in ArcGIS, and finally you find those new layers. First layer is the layer, and the second layer is the case layer. And now you have to get the 10-meter distance from the network layer. And this is our final case area of the 10-meter area. So to create this, follow the steps. First of all, network analyst, select new service area, and then make new layer in the service area. And after that, you will find facilities for your lines. And first of all, you have to load the facilities. So you have to go to location, and here select the station. Once
So here we are doing the network around metro station, commuter rail stations. So we wanted to identify a 10-minute accessible area around 10 minutes by driving distance. So that's what we're trying to do. We're not just drawing equal distances, but we're drawing driving distance. And then if you're examining these as locations affected by commuter. So we wanted to look at areas, property values in that, and also traffic congestion and other things. But we wanted to look at how property values change for homes in this 10-minute driving area versus the rest of the city. Because again, this is the influence area of the train station versus if they're outside the influence area of the train station, how did the prices change? Because in Florida during this time, prices increased everywhere. So we wanted to identify a control and a case. So we wanted to identify where are property values changing because of the train station TOD versus locations where, okay, what is the baseline change? If there is a baseline change of 12%, if your areas around public transit only change 12%, then there is no increase per capita. So that's what we wanted to control. So that's what we're trying to do.
We have to edit the property of the service area. So to go properties and you have to provide the impedance. Impedance will be the minutes. Then you have to provide default break. You have to put 10 percent set in 10 minutes per distance. And then you have to provide the time to day and time to week. And then the 17 polygons here. Now we have to solve it. So we have to click the solve, and once it is solved, you will place it here. You need to export the layer, and the exported layer will be basically. Now select the control area. In our study, we selected 20 to 30 minute time as our auto threshold. The census tract located within this 10 minute threshold area were selected to the immediate control. Here, the blue region is our auto threshold. Control area selection procedure is almost same at the base area. Here, we put 20 and 30 minutes before break option instead of 10 for case area.
So what we're trying to do here is 10 minutes in the influence area, we said. So we wanted to find similar houses or similar properties away from 10 minutes. But at the same time, we did not go too far. So we said we look for time window between 20 and 30 minutes from the station. So we created an area. So this green area was excluded because this is the 20-minute boundary and the blue area is the 30-minute boundary. So then for all the speeds. So we did it for multiple speeds because the roadways are different speeds. Right? When you're going from here, for example, they're going from here to here. Some roads will be 20 minutes, some roads will be 40 minutes, some roads will be 50 minutes. So the speed limit, the initial table that was created, that is to tell if the link road speed limit is 40. We assume average speed is 35 miles on that link.
Okay, so that's speed you are
That's how we are getting out 10 minutes. Yeah, so based on the assumed speed, we can get a time for each link, right? If the link is half a mile and the speed limit is 50 miles, so we are assuming 45 miles, so we get a time to traverse that distance. So again, whenever we are doing network distance, we need to figure out some way of capturing speed. We don't know, we don't have data on speed for everything, right? So we are assuming, making some assumptions to get that time. So we are not blindly assuming the same time, same speed for the entire trip, right? So we are assuming based on the speed limit on that link. Yes, it could be different. Some people go higher, some people go lower than speed limit, but at least we are not assuming average speed is 45 when only 20% of the trip happens on a 40 to 50 speed, right? So that's the reason for this.
So when you edit the properties area, we find that default rates, and in case of case, we provided 10 here, but here you have to provide 20. And just press OK. remaining steps will be exactly the same as the case area. And now we have generated the case area and the contour area. Then you have to calculate the geometric chain that will follow the steps of the property value change we have discussed here. And for the other is the procedure.
So this project again, link is available online. The report also has very good details of how we did all of the GIS work. If any of you are interested or looking for resources, this could be a good source for you. That's why I wanted to show this. So in this project, we did how job accessibility changed as a result of a commuter rail project that was completed in Orlando. So the commuter rail had 15 stations. When we look at different benefits, we look at how commuting time changed, what is the transit travel time savings from the project, okay? And what is the value to the community because of changes in property values. So across most measures, the addition of commuter rail did not make any difference. If you look at the change in condition, they had about 4,500 riders per day. Okay, so in a city like Orlando, that does not add amount too much. I think the travel time improvement was like 0.001 minutes or something like that. Because you're only taking 4,500 vehicles up. You have millions of vehicles on the road, so that doesn't change. So over using every metric, the project was a failure in terms of additional transportation. But if you look at the change in property values, the value addition because of public transit. In the US, especially in the southern part of US, people don't like to use public transit, but they like to live around public transit station because it brings in accessibility, right? There is retail, shopping that comes around that, a lot of condos come around it, the property values. So the three counties that funded the transit agency, so the funds for the commuter rail, some of it came from federal, but everything else came from the counties. So three counties put their money, and we were able to show that they're actually getting the returns back because new developments have come around these transit stations. So which were vacant before. They were not paying any property taxes before. So the counties were getting no income. Now they put in money to fund the agency, fund the train station. But now because of the stations, a lot of new developments have come up and the revenue generated for these counties is substantially significant. To the point that there is a positive ROI for the investment. So again, whenever the reason I mentioned this is whenever we look at transit investments, especially in the Western world, we focus on transportation impacts. Yes, there are transportation impacts, and we want them to be significant. We want them to be large. Right? We don't question that. And it would be nice if 100,000 people are using that transit service, the commuter rail service. But even if that does not happen, there are other non-transportation benefits that can outweigh the costs that go into building that infrastructure. So, if we can convey that message to people who live in these regions, they will recognize the value of transit. Again, the reason public transit is not used well is because it does not serve many locations. What it does is it connects one part of the city to another part of the city only during peak hours. I mean, but people don't just think about life in the peak hours. They need to go there. If they end up working longer, they don't have a car suddenly, now they have to come back home. They went to the train in the morning, but if they cannot get out of work on time, that psychologically does not encourage people to use public transport because they're like, yeah, it's there from 3 to 5. If I get delayed, I can't go. So again, these are some challenges. So, but there are a lot of non-transportation benefits that allow for bring a lot of return on investment. So I think some of the methods we show. So this project is here. This is the project. So we evaluated the community building effectiveness of transportation investments. So it's a three-phase project we did for the Florida Department of Transportation, and it was predominantly looking at using GIS to figure out how property values change, how can we identify job accessibility around a station, how travel time has changed. So these are the different aspects we did. So if you are interested in GIS-based resources, you can look at that project.
In this project, on one hand, you are saying that the property value change and there is settlement and there is change in land use around the area. and there is no significant change in ridership across the country. So either one should be the consequence of the other, and if it doesn't happen, that shouldn't sustain. I mean to say that, for example, there is an expectation that there will be a lot of activity and there will be a movement across that line. And that
It takes time. Right? It takes time for so new communities are coming. So they're just moving there. You have to be patient to see ridership change. It will change. It will grow. There will be, but it's not necessary that all of those people are working in the route. So this is a north-south train station, train corridor. It connects 13, but Orlando is like 60 square miles.
so maybe the gestation period will be longer and we need to wait.
It is possible. No, I'm saying I don't care what is the ridership for the future also. Even without that, just building those stations is creating revenue for the counties because it becomes a center. Those stations become centers of activity for different reasons, and then retail and establishment comes. That doesn't necessarily feed into transit. Again, I cannot help with the culture. I cannot help with why people are not taking transit. We cannot change that. But you cannot focus purely on transportation benefits and say this is working or this is not working. You also have to look at a holistic evaluation is necessary before you call a project a success or a failure. That's what I mean. Yes, again, there are a lot of mistakes they are making in the industry. So they say they are not increasing the train schedule beyond 6 p.m. in the night. And in Orlando, in summer, it gets dark at 8:30. I mean, if people don't even realize it's 6 o'clock before even when it's 7 o'clock. Also. So what I'm saying is, and there is no coordination of Sunrail with the public transit system. The buses, there is no coordination. Like, there is a bus comes 5 minutes after the Sunrail leaves, and there is only one Sunrail every 20 minutes or 30 minutes. I mean, how hard is it to coordinate? But they don't do it because again, there are politics. There are
Kind of surrogate investment to make property tax.
yes. So if you are the county, if you are a county that is putting in money, you should go ahead and put money because you are bringing something that will increase your revenue substantially. Yes, transit numbers might not be that. So but it's still a valuable investment for counties where there's a lot of rural population, and suddenly this comes in. People don't look at this as rural anymore. They look at it as, oh, this is a hub. We can actually live around this. So developers come in and build apartments and homes. Because again, it's a little different than in India. In India, space is a premium. In the US, it's very different. You can buy 1,000 acres for a very little price. Unless there is a home or a resident retail unit there is no value for the land in that part. So that's the change. Okay, so yeah, we take pause. Yeah, and I think we can get to okay, thank you. So please download the data and get so
We already have that.
okay, then it's great. So we can start working on the boards.